Hello everyone. Welcome you all to live session one of NPTEL course Fluid Flow Operations, taught by Professor Subrata Kumar Majumdar. And my name is Nagvan Sai Kumar. I'm going to be teaching session for this course. So every day we'll be having a live session at 6 p.m. Every Tuesday. Okay, so we'll be discussing some concepts that were discussed in the class earlier in the class by Professor, and also we'll try to cover some of your doubts, be related to problems or theory part. We'll try to cover them in this 2 hour sessions. So this is going to be from 6 o'clock to 8 p.m. And I hope all of you received a link. All right. Okay. So this is going to be the course outline. We'll be following this. First, we'll be going through characteristics of a fluid, followed by fluid statics. Then we'll understand fundamentals of flow, one-dimensional flow, flow of viscous fluids, and then we'll also discuss about different losses in pipes, okay, and flow in water channels, drag, lift, cavitation, dimension analysis, and law of similarity, compressible flow, measurement of flow, and also multi-flow phenomena and its applications. Okay, so we'll be covering this over a period of 12 weeks. And during any point of time, if you have any doubts in a particular concept or maybe in some problem, you can ask me. I'll try to solve them in that particular session itself, or if not, I'll try to solve them in the next session. Okay, so today we'll be sticking to basic introduction of what is a fluid, what are the different type of fluids that we have, and what is the history of fluid flow operations. Okay, so this is, today it's going to be more of a theoretical class, okay, or theoretical session where we'll just discuss the basics which were taught by professor in the in the module. We'll just try to have a recapitulation of the entire course. Okay. So what is a fluid? So fluid is nothing but a subset of matter that continuously deforms under an applied shear stress or external force. So what are the different type of fluids that we have? So fluids can be liquids, they can be gases, okay, and we also have plasma. Plasma also comes under fluids, and some to some extent we also consider plastic solids as fluids. Okay. And coming to type of fluids, these fluids can be categorized into two different types. One is incompressible fluid, and the other one is compressible fluids. Okay, we'll look into the type of fluids in detail in the following sessions. Okay, but for now, fluids can be categorized into two types, that is incompressible and compressible fluids. And incompressible fluids can be further divided into Newtonian and non-Newtonian fluids. Okay, so incompressible fluids are nothing but fluids whose density doesn't change. Okay, density doesn't change or doesn't vary. And for compressible fluids, it's the opposite, is density varies. Okay, so this is a classification of type of fluids, and also we have different patterns of flow. So we have single flow, we have multi-phase flow. So single flow is nothing but flow of water in a pipe. Okay, so there is only one phase in the fluid stream, and in multi-phase it is a combination, like two different phases flow combinedly. So like let's say flow of water and oil in a pipeline. So it forms a multi-phase flow. And we also have laminar flow, and then turbulent flow, stratified flow, plug flow, slug flow. I hope you might have heard of some of these flows, right? Let's say example plug flow or a single phase flow, turbulent flow, and these are like other categories of flow patterns. So we have bubbly flow, and then churn flow, annular, homogeneous, and heterogeneous. Okay, so we'll come back to all these different type of flows in subsequent sessions. Okay. Uh, Coming to the importance of fluid flow operations. So in chemical engineering, we'll be going through different processes, right? Like absorption, adsorption. Okay. We also use distillation, drying. Okay. So in all these unit operations or unit processes, so one thing is common, that is fluid flow. So in order to use or operate any of these processes, you need basic understanding of fluid flow, or you need to have understanding of fluid flow operations. Okay, how fluid flows in a pipeline, or how does it interact with a gases, or like let's say vapor phase, that is interaction between liquid and vapor phase. Okay, you need to have all these idea of all these concepts. Okay, can someone give me example of day-to-day examples of fluid flow, where fluid flow happens? You can unmute yourself and tell, or maybe you can post them in the chat box as well. Give me any example of fluid flow in everyday operations, in everyday life. Where do you see fluid flow? Anyone? You can type them in the chat box as well. Give me examples of fluid flow which you see in day-to-day life. Fluid can be liquid flow or
What?
gaseous flow. Yeah,
Water taps है.
yeah, water flowing from a tap, and mm,
Toothpaste.
sorry,
Smoke rising from a chimney.
yeah, smoke from chimney. And any other examples? There are many examples, right?
Hair dryer.
Yeah. So here, gas or air is flowing, right? Air is also a fluid, right? So this also comes under fluid flow. And any other examples? So when you are mixing coffee, so that is also fluid flow, right? Any other examples?
Toothpaste.
Toothpaste. So when you squeeze the toothpaste, paste comes out of the So this is an example. This is also an example of fluid flowing, and so similar to this, we also have. So can someone tell me an example similar to this smoke from chimney? So where does smoke come from apart from chimney? Vehicle exhaust. That is also an example of fluid flow, right? Smoke is coming out of your exhaust pipe. And any other examples? We see many examples, right? Evaporation of water in cooling tower. Yeah, this is also an example of fluid flow. And when blood is flowing in your veins, that is also example of fluid flow, right? Blood flow. This also comes under fluid flow, right? Anything else? Any other examples?
So ketchup,
Yeah, ketchup
now we
is
use
also an
daily.
example. Tomato sauce or ketchup, whatever it may be. This is also an example. And also, whenever, so paint, thinner, yeah, there also. So this paint is not an example of fluid flow. Okay, this is not exactly example of fluid flow. There should be some flow of liquid or gas, right? So this doesn't exactly come under fluid flow. When you must have seen aeroplane take off, right? Whenever aeroplane is taking off, air has to pass over the wings of aeroplane, right? So that is also an example of fluid flow. Okay, so we see different type of fluid flows in everyday life. Similarly, we'll also be coming across fluid flow in chemical engineering as well. So as I've told you previously, so in absorption, distillation, drying. Okay, these are all the unit operations, and we also we also have unit processes as well. So in all these cases, we'll come across fluid flow. Okay, so that is why it is important to learn about fluid flow operations. Okay, coming to the beginning of or the history of fluid flow. Okay, so now this is going to be all everything related to years. So which scientists have done like so and so scientists have done so and so work. Okay, so this fluid flow started in Egypt, and this goes back all the way to 4000 years BC. Okay, so transportation of fluids was first discovered in Egypt and Mesopotamia through uh, basically because of irrigation canals. Okay, they used fluid flow for irrigation canals or channels. So from there, the fluid flow operations started. Okay, so they use these irrigation canals to basically transport fluid effectively from reservoir to the place of irrigation. Okay, so they also observe that if you design these channels properly or conduct properly, they observe that you can the fluid flows freely or with less friction. Okay, whenever you're designing these columns effectively, so the fluid flowing will be flowing with less friction or less corrosion. Okay, and from then on, they started designing all these columns, like proper designing of columns, because obviously, whenever you observe that it is taking less amount of energy to flow from one place to another, so then you'll obviously design the system accordingly, right? So that you have to spend less amount of energy for transportation of fluids. Okay, and after this, you must have heard Leonardo da Vinci, right? So Leonardo da Vinci, he used to write everything, right? So in his notes, this goes back all the way to 1450. So from 1452 to 1519. So in his notes, he used to write about movement of water, eddy currents, water waves, falling water, and also destructive power of water and floating bodies. And he also described about hydraulics missionary principle of hydraulics missionary as well, way back in 1452 and 1519. And he also forecasted loss related to drag and also movement of jet or falling water. And he also advocated that observation of internal flow by floating particles in water, that is visualization of water, visualization of flow. And then comes Euler in 18th century. So he laid the foundation for theoretical equations. Euler in 18th century. So he laid the foundation for theoretical equations of flow for non-viscous fluids. So from 18th century, they started developing equations for fluid flow. Until then, they were just designing, or it's like completely conceptual. It's completely conceptual. But from 18th century, Euler laid the foundation for theoretical equations. So they started deriving equations for fluid flow. Okay, so he wrote, or he developed theoretical equations for fluid flow of non-viscous fluid. And then in 19th century, so famous scientists Navier and Stokes, so they developed equation for movement of viscous fluids. So you will be hearing Navier and Stokes throughout fluid flow operations. Okay, and you'll also be using equation derived by Navier and Stokes as well. So they in 1960 they developed equation for movement of a viscous fluid. Okay, and then in 1869, a scientist called Kirchhoff, he's a German physician. So he reported connection of hydraulics to hydrodynamics. Until 1869, people were thinking that hydrodynamics and hydraulics were two different concepts, or two different branches of science. But then in 1869, a scientist named Kirchhoff, so he related, or he connected hydrodynamics to hydraulics to hydrodynamics, and he also computed coefficient of contraction for a jet flow, coefficient of contraction. So you'll be learning all these concepts in the later sessions. Don't worry. Coefficient of contraction for a jet. for the jet flow from a two-dimensional orifice. So it was found to be 0.611. Okay. And then later, Archimedes came. Archimedes also, you must have heard about Archimedes' principle, right? About floating bodies, law of buoyancy. So Archimedes also, Archimedes about floating bodies, and this is famously called as law of buoyancy. Okay, and then there is one scientist, sorry, Roman mathematician, Claudius. So he constructed hydraulic machinery, construction of hydraulic machinery. Sorry, this is not beginning of fluid flow operations. This is about milestones. Uh, Archimedes buoyancy, and the next great achievement was discovery or construction of hydraulic machinery by Claudius. And then we have two scientists who discovered siphon tube and forcing pump, who constructed siphon tube and forcing pump. Okay. So I'll not be going into all the details of like all the milestones that happened. So I'll be only focusing on the most important things. And then there's one scientist who discovered about sorry, who experimentally who conducted experiments on fluid statics to estimate specific weights, and then in 2006 1206 there is a scientist who described various mechanical devices as hydraulic machines, and then there is also discover invention of two-cylinder reciprocating piston pump. Okay, this was done by Al- so he invented twin cylinder reciprocating piston suction pump. Okay, so this was the first this was a turning point for two-cylinder pumps, which led to subsequent discovery of other pumps like rotatory pump. Okay, so there are many other milestones like you must have heard about Pascal, French mathematician. So he also contributed for this fluid flow, and then Sir Isaac Newton also wrote about the effects of friction and viscosity. Okay, and in 1917, sorry, 1713, Isaac Newton discovered contraction in veins of fluid, which basically issued from orifice, and found that at a distance of about a diameter from the orifice, the suction of vein was contracted in the subduplicate ratio of 2 to 1. So you will be coming all across all these terms in future sessions. So I'm not going to cover everything. And there was discovery of invention of piston tube as well by Henry Pitot. And also there's a famous law, Bernoulli's law, you must have heard. So it was proposed by Swiss mathematician Daniel Bernoulli in 1738. Okay, so this is more about milestones. You can go through more milestones in the lecture given by professor. Okay, so now coming to why one should learn about phenomena of fluid flow. Okay, as a chemical engineer, you might be working as a process engineer in future, right? So process engineers are frequently interested in systems involving flow of fluids because you basically have to deal with all the unit operations in a plant, right? So you'll be coming across different flows across these systems. Okay, so there'll be two levels. One is the practical level. Okay, so at this level, you'll be basically doing all the calculations required for the fluid flow in order to design a process. So let's say you want to design a plant, okay, where you are drying something. Let's say you are removing water vapor. Let's say this is a part of a entire flow sheet, and you are supposed to remove water vapor. Let's say the input is, for example, let's say ethanol water mixture. Okay, and ethanol is around 50% and water is around 50%, and this is coming at a flow rate of 1000 liter per hour, and you are supposed to remove water, and the final concentration should be ethanol 98% and water should only have a concentration of 2%. So in this case, you need to design the entire operation, right? So let's say you will be going for either distillation column or whatever process that you're choosing. You have to design uh, this entire process, right, or the part of flow sheet, right? So this is where you will be using your knowledge of fluid flow to do all the calculations. Okay, and in the second stage, that is conceptual level. So you will be using your fundamental understanding of physical properties of fluid, and then you will try to solve the practical problems in both effective and elegant ways. Okay, so first is to design the equipment for by using all the calculations, and then to second step is to solve the practical problems which are occurring in the process. So let's say there is an issue here occurring in this, there is some leakage or something like that. So you need to solve that. So for that you need to understand the physical properties of the fluid as well. Okay, let's say if it is an flammable liquid, so you need to take certain precautions. Let's say if the density, the viscosity of a fluid is very high or very low, so you'll be using a knowledge of fluid properties and then you'll be solving the practical problems. So this is where you'll be using your knowledge of fluid flow. So fluid flow operations, fluid flow calculations. So in the first step we are using fluid flow calculations, right? So this basically include pipe network design as well. So that is sizing of pipes, sizing of pipes, and pipeline for transferring suitable pipelines for transferring fluids within the process. This basically includes pipe network design. This is the first step, right? So it includes pipe network design. So which is basically designing sizing of pumps and pipelines as well. Okay. And then you'll also check the effects of fluid flow on. So if you are changing the flow rate of a fluid, it also affects other parameters, right? So when you are increasing the flow rate, heat transfer will increase. Okay, mass transfer will also increase, and reaction rate will also. Let's say if there is a reaction which is happening in the process, so reaction rate will also be changing, and also separation rate will also be changing, right? Okay, so you'll be understanding effect of this fluid flow on all these operations. Okay, and then you'll also understand characteristics of fluid as well, because fluid characteristics will determine all these things. Let's say if density changes, then these parameters will change. If viscosity changes, again, these parameters will be changing accordingly. If a fluid is having higher density or higher viscosity, then you need to go for a higher rating pump rate. So that is why characteristics of fluid is also important. And whenever you are dealing with fluid flow, you need to have fundamental understanding of concepts like conservation of mass, conservation of energy, and also conservation of momentum as well. Okay, so you need to have basic idea of all these three conservation laws. So this will help you in developing fundamental understanding of fluid flow. And coming to major mathematical descriptions, so we have a few equations in fluid flow. So you need to understand those as well. One is the first one is the continuity equation. We'll be deriving all these equations. Don't worry. Continuity equation. And as I've told you, there is one famous law. It is Bernoulli's equation, proposed by Daniel Bernoulli, and the momentum equation. So you'll be using all these three equations throughout the fluid flow operations. Okay. So let's take an example of any chemical engineering process. So whenever we are talking about process, or let's take an example of a plant. So in a plant, there will be obviously reaction going on. Just when someone is joining. So there will be a reaction happening, and after reaction, you have to separate the reactants and products. Okay, and then you have to purify the products. Okay, so these are the basic steps which will be in a plant, right? So let's draw a block diagram. We have a reactor, so we need to pump the fluid, right? So we'll be having a pump. So this can be either liquid or fluid, whatever it may be. So then after the reaction, it will be sent to a separator, right? So in order to remove reactants and products. So this is the separator. So once you separate them, the unreacted feed or reactants can be sent back to the reactor. Again, here you need a pump to pump them back to the reactor. And the products which are separated, they'll be again going to a separator or a purifier. Okay, depending upon your need. So let's say you have two to three different products, then you need a separator, obviously. But let's say you only have one product and there might be some impurities along with it, then you will be needing a purifier like distillation column, some whatever it may be. So you need a separator or a
purifier. So you'll be having your product and then you'll be having your byproduct. So do you think at any point of time in this entire flow sheet, will you be coming across a situation where you will be needing fluid flow operations or knowledge of fluid flow? Will you be needing knowledge of fluid flow? Obviously, right. So at every point of time, be it a reactor or let's say unit operations or unit processes, you need knowledge of fluid flow. And also, even when the fluid is flowing in the pipelines, you will be needing knowledge of fluid flow operations. Okay. So first one, what is the relevance of fluid flow to design of for design of process unit? First is to design pipelines. Okay. So only if you connect one process to other process, only then fluid will be flowing, right? So in order to transport fluid from one place to another place, you will be needing design of pipes. So you cannot construct these pipes randomly, right? So you need to construct in such a way that you will be needing minimal amount of energy to pump them from one location to other location. Okay, and also you need to keep in mind about the corrosion effects. Okay, uh, like you'll be coming across different parameters. So corrosion, you need to take care of friction as well. Okay, and then comes pumps. Okay, in order to transport liquid from one location to another location, you obviously need pumps in order to provide energy for fluid to flow, right? So pump will make fluid flow from one along the pipes from one location to the other location. Okay. So according to your needs like flow rate, pressure required, according to that you will be choosing the rating of these pumps. You must have heard like 1 HP pump, 1.5 HP pump, right? So that is decided based upon your needs, like the required flow rate and also required pressure. So apart from this, fluid flow operations also have many other applications. Like so, they'll be used in chemical engineering. Apart from that, they'll also be used in civil and mechanical engineering, and meteorology and ocean engineering as well to know the weather patterns. So basically, clouds or air will be flowing from one region to other region, right, across the world. So you must have seen that clouds will be moving across the cloud, right? Globe, right? So that is that you need to have understanding about that. You need to have understanding. You need to understand fluid flows, basically. So it is used in meteorology and oceanology to understand, as I've told you, weather patterns and also to understand ocean currents as well. So this is also fluid, right? And then in medicine as well to understand blood flow and you can also use knowledge of fluid flow operations in software industries like Fluent, Console, OpenFOAM. Like when you're simulating plant, you'll also need knowledge of fluid flow operations. Okay. So this is about importance and history of fluid flow. So coming back to our fluid. So we all understood what a fluid is, right? So now what is an ideal fluid? So when we are talking about gases, in our 10th or inter, when we're talking about gases, we used to always compare these gases with something like ideal gas fluid. So this is something which forms the reference. Okay. So similarly in fluids as well. So fluids is a broad spectrum, so which includes both liquids and gases. So even here we have something called ideal or perfect fluid. So this is again non-existent, similar to ideal gas. This is also non-existent, and it is an resident fluid without either viscosity or compressibility. So it cannot be compressed, and it does not also it also doesn't have any viscosity. Okay, zero viscosity. Such a fluid is called ideal fluid or perfect fluid. And sometimes Fluids with compressibility are also considered as perfect fluids, but in that case, they should be having zero viscosity. Okay, again, this is also a non-existent fluid. So you'll also consider fluids with compressibility and zero viscosity as perfect fluids as well. So just in order to put this in simpler terms, all the liquids or let's say fluids which obey Boyle's and Charles' law are called as perfect. Sorry, this is particularly for gases, not for liquids. So gases which obey Boyle's and Charles' law basically called as perfect or ideal gases. So Boyle's and Charles' law is nothing but ideal gas. So you're combining both Boyle's law and Charles' law. Okay. So if a gas is obeying both Boyle's and Charles' law, then it is considered as a perfect or ideal gas. Yes. So now coming to the first classification, that is liquids. So in fluids we have liquids, gases, and plasma, right? And we also have other types like plastic solids. So this is the first classification of fluids. Right? So in liquids, molecules in liquids stick closely together, such that the liquid have a defined volume and will not fill a container having a larger volume. Okay. So if you take a 5 liter volume beaker and fill it with 2 liter liquid, it will be occupying only 2 liters, right? It will not be occupying the entire space of a 5 liter container. So because the molecules of liquid will stick closely together, that is why they have a different volume, unlike gases which will be seen in short time. And the volume occupied by liquid varies slightly with temperature and pressure, such as the liquids are essentially incompressible. Okay, so with temperature and pressure, volume of liquids will vary only slightly, or there will be only slight change in the volume. Okay, because we were assuming that liquids are incompressible, right? Liquids are incompressible, right? So that is why there will be only slight change with temperature and pressure. And liquids also form interfaces with gases. So these gas sometimes can be their own vapors and with other immersible liquids as well. Like an example of oil and water mixture, they'll be forming an interface, right? So liquids can form interface with either gases, their own vapors or with other immiscible liquids. And also liquid forms a free surface while gas does not have it. Okay, so these are like, and coming to liquids, we have Newtonian liquid and we also have non-Newtonian liquids. Okay. So there is a law in fluid operations. Tau is equal to mu into du by dy. We'll be going through this derivation as well. Okay, so tau is shear stress and this is constant viscosity and this is strain. Okay, so if the shear stress is proportional to the strain caused in the fluid, then it can be considered as a Newtonian fluid. Okay, and in non-Newtonian case, this will not be proportional to strain. Tau will not be proportional to du by dy. So it will be, and one more thing, these fluids will exhibit time dependent current viscosity. So you will be changing. Okay. So tau instead of mu, we'll be using K. And this is simplify this. This can be clubbed into one term. That is apparent viscosity. So these two terms can be clubbed together and call it apparent viscosity. That is equal to dA by dy. This is again velocity gradient on shear, also strain or velocity gradient. Okay. So whenever there is a fluid flow, stress which the stress in the fluid will be proportional to the strain for returning liquids, and for non-returning, this will be a bit different. Tau will be equal to apparent viscosity into strain caused in the fluid. So examples of returning fluids are water, alcohol, glycerin, or glycerol, and thin motor oil. So these are enough. And apart from this, so as we're talking about liquids, I'm only giving examples of liquids. But apart from this, air is also a returning fluid. Okay. And coming to non-returning fluids, examples of non-returning fluids are nail polish, whipped cream, ketchup also comes under example of non-returning fluids. Okay. And that is also an example of non-returning fluid. And we have latex paints. These are some examples of non-returning fluids. So we'll discuss these fluids in detail in the following sessions. Okay. As I've told you, for non-returning fluids, viscosity is a time-dependent variable, right? So if you draw a graph between viscosity and shear rate, so for returning fluids, this doesn't change. Even if you are increasing the shear rate, viscosity should not be changing, right? So it will be a slightly. But there are other fluids for which the viscosity will change with application of shear rate. So for them, you can have two types. One will increase, the other decrease. So this is called shear thinning liquids or fluids, because with shear viscosity is reducing, right? So this is called shear thinning, and this is called shear thickening liquid. So liquids which show this type of behavior are called shear thickening liquids, and liquids which show this type of behavior are called shear thinning liquids. Okay, we have again these again classified into different types of non-organic fluids. Then we have pseudoplastics, we have dilatants, we have non-bigger plastics, non-ideal bigger plastics, ideal bigger plastics. Okay. We covered that in the later sessions, but I'll just give you an idea of how they will be behaving. So if you draw a graph between stress and strain, right? So for return fluid, this should be proportional, right? Tau is proportional to dV by A by right. So it will be a straight line. But for other liquids like non-tangent, so we have one, four different types. Okay. So this is shear thinning liquid. This behavior should be shear thinning. So here we this graph was between viscosity and shear rate, right? Now we are drawing graph between shear stress and shear rate. So this is how it looks for shear thinning, and this is how it looks for shear thickening. And this is also called as pseudoplastic liquids, and these liquids are also called as dilatants. And this is the behavior of liquids which are called bigger plastics. So if you observe, all these gases starting from the origin, but this is starting from a particular y-intercept, right? So that means only after applying a certain stress, this liquid will start flowing. So liquids, these liquids will start flowing as soon as you apply stress. Okay, but this particular liquid, that is bacon plastics, will start flowing only after application of a certain amount of force. Okay, for example, paste. Okay, if you take the example of paste, so this will not be moving right initially. Even if you apply slight amount of pressure, it will not be moving. Slight amount of pressure. You have to cross the threshold. You have to apply this much amount of force. Only after that it will start flowing. Okay, so this type of fluids are called Bingham plastics. So toothpaste comes under Bingham plastics, and also chocolate comes under Bingham plastics, and clay suspensions. All these liquids comes under Bingham plastics. Okay. And then we have a second category is gases. So gases is the second classification of fluids, right? Second type of fluid. So this is completely contrast to liquids. So in liquids, all the molecules will be held together, right? But whereas in gases, molecules will be free to move. They will be moving apart from each other and will be completely filling a container. Let's say if you fill 2 liters of gas in the 5 liter container, these gas molecules will be occupying the entire container. Okay, because they are free to move and they don't have any force of attraction between these molecules. These gas molecules differ from liquids in two significant respects or aspects. Firstly, liquids are incompressible. Okay, for most of the cases, liquids are incompressible, but whereas gases are compressible. Okay, this is one difference between liquid and gases. And the second difference is that liquids have higher densities. Okay, when you compare them with gases, they have higher densities, and whereas gases they'll be having a very low density. Okay, which basically you can ignore the density as well of a gas. Here are two basic differences between gases and liquids. And now coming to types of gases, we have two different types. First one is natural, which are present in nature, as the name suggests, and then we have artificial or synthetic gases. Okay. So natural gases again, there's a sub classification as well. We have elemental gases. Elemental gas is nothing but hydrogen, oxygen. Okay, they exist in their elemental form, right? Nitrogen. Okay, all these gases comes under elemental gases. Then we have compound gases. Okay, so can anyone of you give examples of these compound gases? There are many compound gases in nature. Any examples of compound gases? Examples of
Carbon dioxide,
carbon dioxide comes in a compound gas. And then
ammonia,
and methane is also a compound gas, naturally compound gas, and sulfur dioxide is also a compound gas. There are many examples. And coming to artificial or synthetic gases, can anyone of you tell or give an example for artificial gases? These are man-made chemicals or man-made gases. Can you give any example of this?
chlorofluorocarbons,
Exactly. CFCs are hopefully example for synthetic or artificial gases. So these are the different type of gases that will be coming across. And then the third classification is plasma. Okay. So plasma can be obtained by heating or subjecting a natural gas, neutral gas to strong electromagnetic field to a point where it completely ionizes and becomes increasingly electrically conductive. Okay, so you have to heat it to such a temperatures such that you can heat it or subject it to electromagnetic force, electromagnetic field or force. Okay, such that it will be completely ionized and becomes increasingly electrically conductive. So, did you ever observe signboards or let's say, have you ever heard of, about neon sign lamps, neon signboards? They'll be glowing. They'll be glowing, right? Have you ever heard of these neon signboards or neon sign lamps? Okay. So what they basically do is that. So let's say you want to write some name or something like that. Okay. So what they do is that they'll be preparing a lamp in this shape. Okay, and they'll be filling it with neon gas, and then they'll be heating it or exposing it to strong electromagnetic field. So we can either heat it or expose it to electromagnetic field. So after a certain point, it will be completely ionized, and then it starts glowing. This neon lamps they will be glowing. That is because of partial ionized plasma in these pipes or tube lights. Okay, and also if you observe interior of sun, you cannot observe it. So in the interior of sun, so you'll be finding fully ionized plasma as well because of such high temperatures. So the gases present in sun they'll be completely ionized and they'll be existing in full ionized plasma state. But whereas in the side modes, you cannot go to such temperatures, so it will be in partially ionized state. Okay, like partially plasma state. Okay. And you'll be using this particular phenomena in different applications as well, like in plasma television. So you'll be using the same technique, and also there is something called plasma etching. You'll be using the same technique in that. You must heard of this plasma television or plasma TVs. Okay, so they'll be using the same phenomena. They'll be heating or they'll be exposing the gas to electromagnetic field, and then it starts. It'll be changed to plasma state, partial plasma state. And then one important topic is future dimension. So whenever you are weight any course, you have to understand future dimensions of all the constants or terms that will be coming across in that particular concept. Okay, so again, I think I don't have to stress much on this topic. So you'll be basically having three different systems, right? MKS, CGS, and SI units. SI units is basically developed from MKS units. Okay, we have MKS, CGS system, and SI units. So this is basically derived from MKS units itself. Okay, so MKS units is nothing but in MKS system we will be using meter for length and kg for mass and seconds for time. And in CGS for length we will be using which what are the units for length in CGS? What are the units for length in CGS system? I hope all of you know about CGS and base systems.
Centimeter, gram,
Centimeter
second.
and gram per second. Okay. So similarly, we also have units for other parameters like ampere. This is for measuring electrical current. Okay, and Kelvin for measuring temperature. Moles for measuring mass quantity, and candela for measuring intensity of light. Okay, and coming to dimensions, we'll be representing these units in a form. So we'll be indexing numbers of combination of base units and express them in a certain physical quantity. It's called dimension. Let's say, take an example, any example, let's say force. Force is nothing but, what are the units of force? What are the units of force?
Newton, dyne,
Newton. Can you expand this Newton?
kg meter per second square.
kg meter per second square. Okay. So if you write this in dimension form, so it will be L M T bar
Minus 2.
minus 2. Okay. So similarly, we'll be coming across different constants and also different parameters in fluid flow operations. Okay. For example, viscosity. Okay. You'll also be coming across density. Okay. There are the other parameters. So sometimes you have to, whenever you're supposed to check the consistency of the equation. Okay, let's say you have an equation. Let's say x is equal to y or m into c x d by x d by a. So you have to check the consistency of the equation. If it is an empirical formula, this doesn't work. But if it's not an empirical formula, then you can use this dimension analysis or you can use this dimensions to check the consistency of the equation. And coming to the last topic, that is basic properties of fluid. Okay, so we need certain parameters, right, of fluid. That told you initially, characteristics of fluid are very important. Whenever you're doing any calculations, characteristics of fluid are very important. So let's see some of the basic properties of fluids that are important in the calculations for the calculations that we'll be doing. So one is density. I hope everyone knows about density. Density is nothing but mass per unit volume. Mass per unit volume of a material. This is called density. And SI units are
Per meter cube. Okay. So density of a material, how does it vary with temperature and pressure? So for liquids, you can consider this to be constant. For you can say this is independent of pressure. Okay, this is independent of pressure. In case of liquids, this is only for liquids. Okay, but whereas for gases, density will depend upon pressure. Okay, this is a function of pressure. Okay, if you increase the pressure, density will change. Vice versa. If you decrease it, so it will be changing. And the next important parameter is specific gravity. Can someone tell me what is specific gravity? Specific gravity. What is specific gravity? I'll write the formula as well. This is specific gravity. Specific gravity is equal to density of liquid by density of water. So this is nothing but ratio of density of a material to density of reference material. So in this case, most of the cases we'll be taking water as a reference material. That too, water at 4 degrees centigrade. Okay, so at 4 degrees centigrade, density of water will be 1. So in most of the practical cases, we'll be taking water at 4 degrees as the reference material, and then we'll calculate the specific gravity. And most of the cases, this will turn out to be the density of the material itself, because anyway rho will be equal to 1, right? So specific gravity will also be equal to 1. Okay, and then there's API gravity as well. Okay, so it is a measure of how heavy or light a particular liquid is compared with the water. Okay, API gravity is nothing but 141.5 by specific gravity minus 131.5. Okay, and the final answer will be in degrees. So can someone tell me where you'll which industry you'll be using this API gravity? There's a specific industry where they'll be using API gravity. Which industry uses API gravity? Which industry uses specific gravity? Sorry, API gravity, not specific gravity, API gravity. Petroleum industry,
Petroleum oil.
yeah, petroleum industry uses API gravity as the reference unit. Okay, and if a particular liquid, let's say, take an example of oil, which is having specific gravity of 1. Okay, if the specific gravity of an oil is 1, that means density of oil, sorry, yeah, if a specific gravity of oil is 1, then that means density of the oil is equal to density of water rate, because specific gravity is equal to density of liquid by density of water. Okay, so if specific gravity is equal to 1, then that means density of oil is also equal to 1. Okay, so in that case, API gravity will be equal to 10 degrees for that particular liquid. Okay, so if API gravity of a liquid is greater than 10, okay, if it is greater than 10, then it is considered as lighter and will be floating on water. Okay, so let's say if this is water, and if oil or if a liquid is having API gravity greater than 10, it basically has lower density and it will be floating on water. Okay, and if the API gravity is less than 10, okay, it says that the liquid is heavier than water and it will be sinking, or it will be below the water level. Okay, and we also have a specific volume, specific weight, specific volume. Specific volume is nothing but 1 by density, or inverse of density, reciprocal of density. This is called specific volume. And then we have specific weight. Okay, specific weight is nothing but weight of a sample by unit volume. Okay, this is represented by gamma. This is specific weight, and then we have one important parameter, that is viscosity. And there are two type of viscosities again. One is dynamic viscosity, and sorry, one is kinematic viscosity. Another one is dynamic viscosity. So kinematic viscosity is represented as mu, and this is as okay. These are two different terms: dynamic and kinematic viscosities. Okay, so kinematic viscosity is dynamic viscosity upon density. Okay, so accordingly, I think you can calculate the units. So this has mu has units of Pascal second. Okay, and the kinematic viscosity has units of meter square per second. Okay, and if you write this in CGS system, it will be centimeter square per second, and this is also called as Stokes. Okay, 1 centimeter per second is also called as Stokes. So yeah, and coming back to this, viscosity is nothing but a quantity expressing the magnitude of internal friction in the fluid. Okay, it's nothing but a quantity expressing the magnitude of internal friction in a fluid. Okay, this is measured as force per unit area resisting uniform flow. Okay, and then we have surface tension. So surface tension is the internal pressure of a spherical drop. Sorry, excuse me. Going to pause it a moment. Okay, the other parameter which is of importance is the surface tension. Okay, and then we also have capillarity. Capillary is capillary is a phenomenon where liquid will be rising through a small opening. Okay, let's say you have a capillary tube and you if immerse this in a liquid. Depending upon the properties of a liquid, this liquid will be rising through the capillary tube. So this phenomenon is called phenomenon is called capillarity, and this is one of the important parameter of liquid or fluid. Okay, then we also have compressibility. Okay, so we'll be measuring that in terms of bulk modulus. Bulk modulus is K, which is nothing but del P by del V into V. Okay, so with a given pressure, how much volume is changing? It is how you will be calculating the compressibility, right? All is also written as minus V into dP by dV. Okay, and bulk modulus is also written as compressibility is written as 1 by K. Okay, we'll move on to some problems now. This is more or less about the introduction part. We'll be starting our actual classes from next week. Okay, we'll try to cover some problems as well and some important concepts. Okay, so now let's move on to this small questions part. So first question: which prominent scientist investigated the effect of friction and viscosity in reducing the velocity of a running water? Uh, Option A: Albert Einstein, Sir Isaac Newton. C: Daniel Brownie, and D: Lord Kelvin. So if you remember this, it's Sir Isaac Newton. Options are missing from the second question. Okay. Let's go into third question. This again you'll be coming in future classes. So if you know, you can answer it, or I'll skip this question. Pikachu will be dealing with Pikachu in the future classes sessions. Okay. Yeah. I think you can answer this. Which of the following is not a characteristic of an ideal fluid? In case of an ideal fluid, it should be inviscid fluid. It should be inviscid. It should be
Is it
incompressible.
this?
Sorry. So correct answer is rotational, which is not a characteristic of an ideal fluid. So it is irrotational. And fifth question, which of the following statements is not correct? Fluids can be treated as continuous isotropic substances. Liquids form interfaces with their vapors. Gases form a free surface. An inviscid fluid with compressibility is occasionally called a perfect fluid. Which of the following is not correct? Does gases have a free surface? No, right. Only liquids will have free surface, right? So option C will be the wrong answer. Yeah. Plasma can be obtained by subjecting a neutral gas to strong pressure force, gravitational field, shear stress, or electromagnetic field. We discussed this
Electromagnetic
point.
field.
Electromagnetic field.
Yeah, electromagnetic field, option D. To calculate specific gravity, the reference fluid in the case of liquids is which of these is used as a reference fluid? Water at 25, water at 4,
Water at
water at 4.
4.
So that is used as reference liquid. So at this temperature, density of water will be 1. Okay. So the higher the API gravity, the dash is the fluid as compared to water. Heavier, lighter, no impact on density, none. So if API is higher, or let's say if it is greater than 10, so what would be the nature of the fluid? Is it lighter or heavier than water? If value of API is more than 10, not degrees Celsius, it is degrees. So if it is more than 10 degrees, then the fluid is considered as allied formula as well. 141.5, I guess. I'm not sure specific gravity. So if this is if specific gravity is equal to 1, then API will be 10. Okay. So if API is greater than 10, then that means what should be the denominator? It should be a lower value, right? Only then you'll be having a greater difference, right? This difference should be more than 10. So that means this should be a lower value. And specific gravity is nothing but density by density of water at 4 degrees centigrade. So this will be anyway 1. That means density is less than the density of water, right? So then means it is
Lighter than water. Yes or no? If you don't understand, I can repeat it.
yes.
Do you want me to repeat it? Okay, so API gravity
Mm,
is nothing but what is the formula? I'll just say the exact formula. 141.5, right? Yeah. 141.5 by specific gravity minus 131.5. Okay. Let's take an example of oil 1. Okay. So this oil 1 is having density of 1. Okay. Or let's say O1. In case of O1, density is 1. Then specific gravity will be equal to 1, right? Because specific gravity is nothing but density of liquid by density of water. Okay. It's nothing but 1. So specific gravity will also be equal to 1 in the case of O1. So in that case, API gravity will be 141.5 by 1 minus 131.5. So this will be 10 degrees, right? So API gravity is 10 degrees for liquid O1, which is having density of 1. Okay. So let's take the second case of O2. This oil 2. Okay. So let's assume that density is 2, which is greater when compared to density of liquid, right? So specific gravity will be density of liquid by density of water, and this will be 2. Okay, because 2 by 1 is 2. So now if you calculate APA for oil 2, APA for oil 2, it will be 141.5 by 2 minus 131.5. Can anyone tell me the difference? What is the value of this?
5.
5. Okay, I'm just writing down what you are saying. Okay, so in this case, API gravity is 5 degrees. Okay, let's take another example of O3. So let's say the density of this oil is only 0.5, okay, which is less than density of water. Okay, so specific gravity will be again density of liquid by density of water, which is nothing like 0.5. So if you calculate APA for this particular liquid, what will be the value? 141.5 by 0.5 minus 131.5. What will be the value?
20.
So if you observe, liquids which are having density more than water are having APA gravity. So if density, let's for liquids which are having density more than water, they are having lower APA, which is less than 10. Okay, and liquids which are having density lower than water, they are having higher APA, which is greater than 10. Okay, this is basically inverse relation. If density is more, APA will be less than 10. And for liquids which are having density equal to water, they are having an APA of 10. Okay. So in this case, if the API gravity is higher, let's say API is higher in the sense, let's say it is greater than 10. So what will be the nature of liquid? Is it heavier or lighter than water?
Lighter.
It will be lighter. So you understood the concept, right? So if a liquid is lighter than water, it will be having API gravity higher than water. API and density are inverse relation. Density is less than 1, API will be more than 10. Density is less than 1, API will be more than 10. And if density is greater than 1, API will be less than 10. It's an inverse relation. Okay. So coming to the ninth question, everyone understood this, right? Or do you, if you want, I can repeat it again.
Understood, sir.
Okay. So coming to ninth question, the viscosity of which of the following increases with increasing shear rate? Again, we have to go back to the graph. This is a graph. Okay. This is a question. Viscosity of which of the following increases with increasing shear rate? So viscosity should increase with increasing shear rate. So those type of liquids are called dilatants, pseudoplastics, Italian or rheopeptic liquids. What will be the answer? So if you are increasing shear rate, mu should also be increasing. So that is shear thickening liquid, right? So what is shear thickening liquid? It's called dilated. Okay. Whenever you're increasing the shear rate, viscosity should increase. So in this case, it is increasing, right? So it is called shear thickening, and shear thickening liquid is also called as dilated. Okay. Option A. Coming to 10th question, what is the relation between compressibility and bulk modulus? Option A, 1 by K inverse relation directly proportional, or K power 2 or 1 by K power 2. What is the relation between B and K, compressibility and bulk modulus?
1/k.
Will be inverse relation, it's 1 by K. Okay. So if you have any doubts, you can ask me, or maybe we'll meet next Tuesday, same time. So from next week, we'll try to cover some problems as well. Okay, and any doubts you can ask me. You can post them in the chat box, or you can ask me. Or if not, we can end the session now, and we'll all meet on next Tuesday, same time, 6 to 8 p.m. Also, you'll be getting. I'll be uploading this video on YouTube as well, so you'll be getting the links as well from NPTEL. As well from NPTEL.